Hi everyone, thank you for joining. In this video we're going to talk about time dilation. So we know that the principle of relativity has shown us that the time must be relative in the sense that the time is not the same for two reference frames moving relative to each other. Right? So what we have here is that now rather than qualitative, this would be a quantitative approach, that we have a clock here. And how does this clock operate? Well, you have a light source which emits a very short pulse of light, and that light is reflected from the mirror and reaches the light detector. And as soon as detector receives that light source instantly emits another light pulse. This is how it works. So this is so-called light clock, right? And our goal is to look at this clock in two different reference frames, S and S dashed. One is moving relative to the other, and see what quantitative conclusions we can draw from this. Right, okay, so if you look at the S dashed frame here, so S dashed frame is the frame where the light is at rest, right? And we want to make a measurement at S dashed frame. So let's have a look at it. So we have the distance h, and then using very simple GCSE formula where acceleration is 0, we will get, according to S dashed, what we will have is that we will have the time, I'm going to call it delta t dashed, is equal to distance, which is 2h because it goes up and down, divided by c, which is the speed of light. So the time it takes, according to S dashed, is delta t dashed, which is 2h over c, where c is the speed of light. Now, to understand relativity, I think it is crucial that we have a good understanding of classical analysis. And let's do a classical analysis first, and then we bring in special theory of relativity. Right, so according to a stationary observer, S, what the person will observe is that because the mirror and the clock will be moving at velocity v, as you can see in this S dashed frame here. So this is what an observer at S will be observing. So as you can see that the mirror was initially here, but now it's there. And then it will be in the final state somewhere there, right? So what we have is we have emission and then detection. And notice that here I said u light. That is the speed of light as observed by the observer at the frame S. So this is classical analysis. Notice, we're not saying this is equal to c. We're not saying that, okay? We're not saying that the light from all inertial reference frame is the speed of light is c. We're not saying that. So this is a classical analysis, and the reason we're doing that, we want to have a better understanding of special theory of relativity. So now thinking about this classically, if you look at it, so this would be here, if you look at this vector diagram, this would be c, the light velocity in the clock, because in the clock we know the light is traveling at speed c, and this is the velocity of S dashed moving away from S. U light must equal to c squared plus v squared square rooted, right? Using classical analysis. Okay, so now let's use a Pythagoras, and we have then h squared is or plus 1 over 2 v delta t squared is equal to half u light, speed of light, delta t squared. Okay, so instead of u light, we sub in half square root of c squared plus v squared delta t squared. So we sub that in there and then there, right? Okay, now if we simplify this, what are we going to have? Well, that would be the same as 1 over 2c delta t squared plus 1 over 2 v delta t squared. And if you notice that we have that cancelling with that, so we will have h squared is equal to 1 over 2 c delta t squared. Well, that implies that we must have h is equal to half c delta t. That implies 2h over c is equal to delta t. That is the answer we have. Now let's compare this with delta t dashed. What was delta t dashed here? Delta t dash is 2h over c as well. As you can see, the classical analysis tells us the time observed by the observer at s dashed frame is the same as the time observed by the observer at s frame. So there is no time delay. So this is what classical physics tells us. This is what classical physics tells us. The time doesn't behave in a strange way that it does in relativity, right? So as we can see classically, both observers experiences the same time. But now let's bring in relativity. So how are we going to bring in relativity into this? Well, to bring in relativity, all we have to do is we get rid of this u light and we replace that by c. Because whether you are observing a train from the platform, train moving with some velocity v, or you're observing, if you are doing the measurement inside the train, moving with the train, speed of light is just c. It doesn't change. Now, this is where we bring in relativity. And now, again, using the Pythagoras theorem for this triangle, what we will get is we will get this equation. We will have h squared plus 1 over 2 v delta t squared is equal to half c delta t squared, right? So now we have for the observer at s, speed of light is the same thing, c. Okay, so we sub in, we know that delta t dashed is equal to 2h over c. That implies delta t dashed times c times a half is equal to h. If we plug that in, so we have half c delta t dashed squared, that's h squared, plus half v delta t squared is equal to half c delta t squared, right? Now let's make delta t the subject. So we have half c delta t dash squared is equal to half c delta t squared minus half v delta t squared. Okay, so let's do some cancellations. Well, the half will go because we're squaring at every point. The half will go like that. So we have c squared delta t dash squared is equal to c squared delta t squared minus v squared delta t squared. So that's equal to delta t squared into c squared minus v squared. So we have c squared over c squared minus v squared. Delta t dashed squared is equal to delta t squared. Yeah. Okay. So let's divide everything by let's multiply everything by 1 over c squared over 1 over c squared. Yeah. 1 over c squared over 1 over c squared is just 1, so we can do that. Okay, we're multiplying that. So that means we will have 1 over 1 minus v squared over c squared. Delta t dash squared is equal to delta t squared. So that implies we have delta t squared is equal to, now if you take in fact square root of both sides, we will have that's equal to delta t dashed divided by 1 minus v squared over c squared square rooted, right? Okay. Now we have a very different time than the than the classical physics. So classical mechanics is quite different, because remember, classically we had delta t is equal to delta t dashed, yeah? But this is quite different. Now, a few things to say about this formulation is that if v is very slow, if v is less than c, one thing to notice is that delta t is equal to delta t dashed over. Now, if v is much smaller than c, that means v squared is much, much smaller than c squared, right? So what we have is that we nearly have 1 minus 0. So delta t dashed over 1. In other words, delta t is equal to delta t dash. So the approximations in classical physics in daily life, if you're talking about bicycles or motorcycles or cars, so it will approximately be the observed times from S frame and S dash frame will approximately be the same, yeah? What is, when you start seeing the effects of this is actually when the velocity of the particle or whatever you're looking at is approaching the speed of light, then you start seeing the time dilation. In fact, let me give a very exciting example. Let's bring in a black hole. Okay, so let's say we have a black hole here. So quite big distortion of the space-time here. Fabric. Okay, so let's say black hole, that's the event horizon. Okay. So, and let's say that there is an observer B, and, well, let's say observer A here. Okay, and at B there is someone close to the black hole. Okay, so what's going to happen? Well, because of the gravitational field strength of the black hole, the person from the reference frame of the person at B, that this person will be traveling near the speed of light, because the black hole, the gravitational field strength will be tearing this person apart into his atoms, unfortunately. So right, so according to B, this person will instantly smash into the black hole, almost at the speed of light, yeah? But what about the person observing this event at A? So this person, A, looks at B, and B seems to him as if it's stationary. And then the person at A gets bored because the person at B is not moving, and he decides to come back 10 years later. And then he realizes there's almost no change. And then he says, why don't I come back a million years later? So he sees maybe little tiny movement towards the black hole, yeah? So yeah, this is, as you can see, this is due to time dilation, that when velocity of the person or the reference frame is really fast, if it's delta t is equal to, if v is approximately c, you have delta t dashed over 1 minus approximately c squared over c squared square rooted, that's delta t dashed over approximately 0. So in other words, this here would take almost infinitely long time, right? So this is where time dilation would be very apparent to the observer, observing, and in this case, observer A, okay? All right, okay. Well, I hope you enjoyed it. I hope you found it interesting, and I look forward to seeing you in my future videos on length, contraction, and some other interesting concepts of relativity. Thank you.